Our last speaker is Rosie Min. She's an AI consultant at Google. She's former senior director at Warner Media. She's also a former senior data science manager at Accenture. She earned her MS in computational finance at DePaul University. And here's a fun fact to know about her. She's a born nerd, but she wants to kind of go into comedian. She wants to be a comedian. So I pointed her to my friend Robert Joseph, Dr. Bobby Joe is what I call him. And Robert Joseph has studied comedy, and he's a comedian on the side. And Julie Grantier, who's still here, she's at the registration desk, she studies improv. And I mention that because that's a very good skill for data scientists, is to practice improv or to take acting classes or to study comedy. It improves the way we communicate. So Rosie Min, we are very thrilled to have you.
Thank you, Beverly, for the introduction. Well, I did sign up for a stand-up comedy class starting in October, so next year when you see me, I probably will do a much better job. It's been a great conference, and I'm so glad to see so many of you actually decide to stay around for the very last session. And I'm so grateful that you don't think a feature store is a mundane topic. Talking about mundane, well, today I'm going to talk about how feature store can save you from the mundane of your life. Work life, I mean. So a few months ago, I was working as a hiring manager for a data scientist role. I had a really good conversation with one of the candidates. At the end of the interview, I asked him, "Do you have any question for me?" "Yes," he said. "I want to know how much time do you expect this role to spend on feature engineering?" And the next day, I interviewed another candidate, and she asked the exact same question. By the end of the week, when I interviewed the third finalist, he asked the exact same question again. So the thing is, this is actually not my first time being a hiring manager, so I told all of them, "Hey, I had great news for you. We actually built a sophisticated feature store so that our data scientists can focus their time on the business problems and building models instead of writing SQLs or ETLs." And you can imagine, after hearing that, all of them are so eager to get this job. And actually nowadays, most of the sophisticated machine learning team have built their own feature store. Like Uber built Pilot, like Airbnb built Zipline, like Netflix built Time Travel. And even the major cloud provider also offer this product. Google, we have the Vertex AI feature store. Amazon has the SageMaker feature store. So now you may have a question. What is a feature store, and how it's related to data scientist work? I've been in the data science practice for over 11 years. And throughout my career, from what I experienced and what I observed from my clients, I found that feature store is really a very common pain point. We all know that feature engineering is so important. As Professor Andrew said, applied machine learning is basically just the feature engineering. But sometimes we feel like the time we spend on feature engineering is a little bit too much. And much of this time can actually be saved. So let's say you work in a really large data science team with over, 20 data scientists. And you want to build a model, you have a list of features, you spend probably 2 months to calculate all of this, and then you're so excited. Then turns out all those features has already been calculated by someone else. It already exists. And more than likely, you probably will find 3 other people is doing exactly the same thing as you did. Let's be realistic. You guys are working for the same company, same team. You really expect your work to be so unique that there's no overlap? So those overlap actually means that there is some redundant work. So all those features are hard to share and reuse, which is actually leading to the redundant work. Another scenario, let's say there is a change from upstream data. Yes, cross-team collaboration. When I look at your face, I bet you guys all have a lot of story to tell about cross-team collaboration. Let's say there's some change from upstream. And out of the 10 data scientists using this data, only 7 of them are aware of it, which means the remaining 3, they will end up using a problematic data in their model. That's not good. And here, we're only talking about model training. Let's bring the model serving into this picture. And that comes our nightmare, which is training serving skew. Training serving skew occurred when you actually say that there's the difference between the performance when you train the model and the performance after you deploy it. What does this mean? You have a perfect model. After you tune and tune and tune, you're so happy with your model, you hand it to the machine learning engineer team, they deploy it, put it into the production, and then you found the model doesn't work anymore. What happened? There are many possibilities here, but one of the most common reasons is actually the data. The data you use to train the model is not the data you use to serve the model. So in a laboratory world, your training data is usually really clean. It's perfect. But when you serve it, the data is a bit messy. Looks like this. So your model still works, but your model only works in the world that is represented by this training data, which is this beautiful, vivid horse butt. And when you serve it, the model doesn't work in the other world, which is the world represented by your serving data, which is this cute little head. So with all those problems, how can we solve them? Logically, you would think, what if I have a centralized place to put all my features? Which means all the team can pull the information from the same location that will reduce the redundant work. Which also means if there's a change from upstream, they only need to change one place, which helps the cross-team collaboration. And if you serve the data, when you serve the data, you just pull the data from the same location where you put the training data that help to avoid this training serving skew. And this centralized location is called feature store. Feature store is a centralized repository for organizing, storing, and serving the machine learning features. The concept is as simple as that. What's difficult is actually the implementation. 3 years ago, when I joined HBO Max team to be the senior director of data scientists, the first thing I did is actually to decide to build a feature store. We released the first version very quickly after just a few months, which including a few hundreds of features that is commonly used in the media industry. For example, what are you watching? What device are you using? Are you watching any TV show that the last episode is still on air, and we know the last episode would be dropped after your building cycle end date? So a lot of complicated features, but it's all like stored there. Whenever our data scientists need to build a model, they just need to go to the feature store and grab it. They probably also need to calculate another handful of features that is unique to their own business problems. But that brings the feature engineer time from a few months to just a few days. So that's the power of a feature store. And you may be wondering, how can I implement a feature store? So here, I would like to talk about 5 topics and share some of my personal experience. Hopefully, this can help you to decide what kind of a feature store you want to design and implement. So before we start, this is an end-to-end machine learning pipeline. And you can see how the feature store fit in. And this is just one example. There's many different ways to implement it. And in this example, you can actually say that we start with the raw data, which is represented by this gray box. You have the batch data, you have the streaming data. And then you have the pink box, which is a feature engineering. You have the batch feature engineering, and you have the streaming feature engineering. And then you just ingest all those data into the feature store. And you put them, you save them, and then you output them to serve the model training and also for the batch inference. And for the online inference, you will want the online serving. And what does online and offline mean here? Offline inference, also the batch inference, they're really the same thing. We just use the word interchangeably. So this means that you generate prediction for a batch of observations on a occurring schedule, for example, hourly or daily. And online inference is really you generate a prediction on demand, typically in real time. You receive a request, you run the inference pipeline, you return the results. And you can imagine that this thing has to be done at a very low latency. Usually you have to retrieve the feature value within, let's say, a few milliseconds. Now comes the question, how does this happen? How can you retrieve features with this kind of low latency? That would lead to this architecture of the feature store. The feature store usually implemented as two databases, one offline store and one online store. Offline store is to serve for the model training and the batch inference, and the online store is for the online serving. And this is the main architecture difference between a feature store and a traditional data warehouse. So the offline store is actually the kind of data warehouse most of you are already familiar with. It processes large amount of data, it's cost effective, it has no requirement on latency. And an online store, on the other side, it has it focuses on the like the speed. You have to retrieve the feature value at like really fast, like really low latency. And then normally speaking, each time you just need to pull the value for one single row. So those requirements, with those requirements, you probably imagine that we actually need a row-oriented database. Oftentimes, it's a key value store. You can also imagine that the price is quite different for online store and offline store. So using the Google Vertex AI as an example, for Google Vertex AI feature store, for the offline storage, it's just 2 cents per gigabyte per month. And for the online store, it's actually 25 cents per gigabyte per month, which is 10 times higher. I still remember when I first built a feature store, I actually started with only half it, which is the offline store. And at that time, there was a lot of engineers in my team try to pitch to me and propose, hey, let's move on and let's build an online store. That's the trend, that's the future. And I have to talk to them, hold on for a second. We were going to build it, but not now. I know it's the future, but without a use case, how can I justify the cost that I need to build this? How am I going to tell my own boss, hey boss, by the way, we just upgraded our feature store to an online store. Oh, there's no use case that requires online serving. We just think it's cool, so we build it. And by the way, our storage cost will go up 10 times next month. Enjoy. So we've been holding that for a really long time until the recommendation team reached out. They really love the features that we created, so they want to use it in their recommendation engine. And I was like, yes, that gives me the justification I need to upgrade my half feature store to the full feature store. Here comes another question. When do you need an online store? Can you just live with the offline store? Let's go through a few use cases. Let's say use case 1. You are supporting the marketing team. And the marketing team want to send out an email 7 days before each user's billing cycle ends. And this email would be sent at 5 p.m. Is this online or offline? Any idea? Yes, offline. Thank you. This is actually very typical offline, 5 p.m., which means it's on the schedule. So you only need to run a daily job to pull a list of users whose billing cycle ends in 7 days. You run the batch prediction on them. You send the result to the marketing campaign tool. That's all. All you need to do is to make sure the job finishes running before 5 p.m. There's no other requirement on the latency. Let's say use case 2. The product team want to add a feature on the app. Let's say you're running a food delivery service, and this feature is to actually give you the estimation on the food delivery time for each of the order. In this case, is it online or offline? Thank you. Yes, this is definitely has to be online. You have no other choice because you kind of need the order information. What are you going to do with offline? Running an hourly batch? Hey, Rosie just ordered something, and based on the hourly batch, just run, we think the estimation time is about, let's say, 15 minutes. Oh, this 15 minutes is based on Rosie's past, like I say, behavior. What she ordered mostly is pizza. Let's take a look at what she ordered this time. Oh, shoot, it's a Peking duck. It takes like 1 hour to prepare. That would be really bad. You are setting up the wrong expectation for the user. So this case, it has to be run online. But actually, a lot of other use cases kind of fall in between these two. For example, you want to run a recommendation engine. It would be great if you have the latest information, let's say what you just searched, what you just clicked in this current session. But if you don't have it, based on what you watched in the past 30 days, I would still have a pretty good understanding of what the user preference is. So in this case, online is better. But does the benefit really justify for the cost that it takes to build an online store? So it will be up to you as the data scientist to determine what is the best architecture here, what is the benefit and the cost that I can get from it. But if you decide to move on with the online store, this feature store would be really powerful for you. And one last thing I want to actually, the next topic I want to talk is actually the batch versus the streaming data. Batch feature, they're the static feature. They're from the historical data. They can be really complex, multiple level of aggregation, multiple transformation. And the streaming feature, they're the dynamic features. They focus on the speed instead of the complexity. So in this diagram, you can actually say that for the online store, they are using both the batch ingestion and the streaming ingestion. Why? Because combining both can actually make your prediction more powerful. Go back to the food delivery service example I gave earlier. You need some online features, the streaming features, sorry. And for example, what did you just order? Which restaurant did you order it from? Those are the information you just collected in the current session. But you also need historical data. For example, how long does it take for this restaurant to prepare the same dish in the past, say, 7 days? What's the average time? So those offline features would actually make your model much more powerful. By combining them, you will actually have the great benefit from both the online and offline. And here maybe comes to another question is, now I only send the batch ingestion into the online store. How about the streaming ingestion? Do I need to send it back to the offline store? That's actually debatable. Well, let's say in a scenario you want to run a batch inference. In this case, you probably don't need the streaming ingestion because what information you need is pretty much already, included in that batch process. But in one scenario, it actually would be beneficial to send the streaming feature, which is send it to the model for the model training. Remember earlier we were talking about the training serving skill. You're using different data for both for the training and for serving that would lead into the skill. So in this case, if you want to solve that problem, you can actually start sending the streaming feature back to the offline store and use it specifically for the model training. That would help you to eliminate this kind of skill. As a matter of fact, I think Uber is doing that. So for all those features that has been generated in real time, they are saving it back to their offline store. So for the future training purpose. Okay. The third topic I want to talk is actually the computation versus ingestion. When we talk about a feature engineering, when we talk about a feature, we just keep thinking about a feature engineering. Naturally, we will think about a calculation, how to aggregate them, how to transform them. But actually, feature store would be focused more on the serving the feature instead of calculating the feature. So you can actually say that more and more feature store provider offers the feature ingestion instead of feature engineer, feature computation. For example, Fist, that's one of the very popular open source feature store. They even call out on their website that FIST is not a computation system. Most people use FIST, actually use it together with another system, which is usually written in SQL. It's actually the same case for Uber, who is actually the first company introduced the concept of feature store back in 2017. So in their case, they also build complicated, like say the ETL, and after each of the project team can choose whether they want to just keep these features private or publish them into a feature store for everyone else to use. So what does this mean to us is after you separate this feature engineer and the feature store, then you can actually have your feature store focus on the serving, and whatever, all the ETL you have been built in the past, it can still be used. So these two really goes together, the feature engineer and the feature store. They are not like one replace the other. And up to now, with this three topic, you probably figured that the feature store is really just like a supermarket for data scientists. You can just go there, grab the information you need, like chips, Coke, alcohol, and then you're ready for your Friday night. You don't care about how the chips is produced, how to grow a potato, how to cut it, how to make it chips. You just go there, grab it, and you can use it for your model. So that's the purpose of the feature store. And the feature store is actually more powerful than that. Another one I want to discuss is actually the time travel. We know the machine learning is all about using the information in the past to predict the future, which means when we build the training data, we have to travel to some time in the past, collecting all the information available at that time, and then train the model. It's critical that you cannot include any of the future information into your model. Otherwise, that would be a data leakage problem. So by having this time travel functionality, you have the ability to query data as it was at any given point in time. And there's two ways to do this time travel. You can do snapshot-based time travel. You can do the continuous time travel. What's the difference? Snapshot-based time travel is just to pick up one cutoff date. Let's say I want to predict the free trial conversion. Then what I can do is, hey, go back to September 1st, give me a list of all the people still in free trial, calculate what happens before September 1st, and predict if they will convert to a paid user. What is the continuous time travel? You will have the sliding windows or expanding windows. For example, my free trial goes from September 1st to September 7th. And maybe your free trial goes from August 20th to August 27th. So for me, my feature would be calculated from September 1st to September 7th. And for you, this feature would actually, using a sliding windows, goes to August 20th to August 27th. So that's a two different way of doing it. And you can see that here, the snapshot-based time travel, it's easier. It's easier to calculate, and it's also easier to maintain. While the continuous time travel is a little bit more complicated, but it also gives you more information. And my experience with this two is when your user behavior are changing rapidly, continuous time travel usually would yield better results because it captured more information. But if your user behavior are kind of stable, like for a lot of traditional companies, you really do not expect that your customer has a lot of activities in a short time. So like the snapshot-based time travel usually yield just as good results as the continuous time travel, and it's easier to compute. So very last thing I want to talk is actually the monitoring and the governance. Imagine this feature store is like a supermarket for the data scientists. As the manager of the supermarket, you have two responsibilities. First, you want to make sure all the users can find the information, find the stuff they want in a short time. Second, you want to make sure that the quality is good. You definitely don't want to constantly sell the low-quality product to the customer, even though it's not produced by you, but it still hurts your reputation. In this feature store example, it's the same. How easy to find the information? If I'm a new joiner, just join the team, and I have a question about a feature, do I have the capability to just find the information immediately? or I have to ping someone to ask a lot of questions. Or even worse, I have to ping a lot of different people, and every one of them tell me different information, and I have to use my best judge to determine how to use it. Another scenario, if I'm a data scientist, I have a long list of the features. How do I know which feature has already been covered, calculated in the feature store? How do I know which one I have to customize it, calculate it myself? So all those information need to be saved somewhere. This problem can be solved by documentation. If you just have a place to save all those definitions and the metadata about each of the feature, how it's calculated, then the problem would be solved. This is also called a feature registry, which is a standard way of just keep the definition and the metadata, which will also serve as the single source of information for the whole organization. Second question, how fast can you detect the issues? If there is something wrong with upstream data, can you detect it immediately? Or you have no control over it, just let the data flow through the whole pipeline, eventually hit the production environment, generate a bad prediction. You just stay there, wait until someone comes to yell at you, and then you find out, oh, there's an upstream data issue. And also maybe there's no issue. It's just the data changed naturally, data drift, which lead to some of the model drift. Were you able to detect it immediately and retrain your model? Again, those concepts are very easy to talk, but in order to really implement it, that would be a lot of work. But if you can really implement it, that would be really powerful. Having this supermarket for your data scientists can really save them a lot of time to do all those calculations, so that your data scientists can really focus their time on the more important thing, which is the business question you want to solve. Okay. So that's the end of my presentation. Here, I just talking about 5 of the topics related to the feature store. I know that I just scratched the surface. Really, I can probably use in the entire session for any of these 5 topics, maybe next year. So, yeah. So with, I think I have still 4 minutes left. Is there any question? No. Oh, yeah.
Is that good? Okay, there we go.
Hello? Yeah, I jump in the middle of it, so you may cover that topic, but let me just ask my question. In case that, I guess the feature store is say I have my own data, you convert it into the feature that can be reused, right? Easily reused. And you provide that kind of infrastructure, that kind of tool set, so that kind of feature can be reused, not limited to a particular project, but can be reused for another project in the future, right? So that's my understanding. I'm not sure whether that's what you talk about. In case, think about this. I have, say I'm dealing with a particular project which has text data, has tabular data, and you convert it into the text data, and you do some say feature embedding, and that's a numerical vector, and other data types like category variable, continuous variable, you also do some transformation, convert it into another embedding, right? And so how do you because data change all the time, the feature store in your feature store is according to your theory, right? You can basically, that's the feature of certain time with certain timestamp. In case, say I'm building a recommendation system, and that kind of feature would not be relevant to the new situation to recommend, say a meeting to a particular person. So my point is the feature when you generate it, say 2 months ago, would be appropriate to use to recommend a meeting to a certain person, the user, right? But after 2 months, you basically need to renew that feature so that you can use the new feature to make recommendation to the user at that time. So I don't know whether you need to recalculate the feature, or how do you deal with that kind of situation? Yeah, that's one of my questions.
Yeah, that's a great question. And I would say, generally speaking, all the feature goes to the feature store. It has to be managed by the team, and they usually would turn it into something that constantly updates. You barely see some feature just stay there and never update again. I mean, some information, like a demographic, you don't expect it to update that often, but every month, every 3 months, they will get update. If you relate it to the user behavior, let's say if you calculate as a one-time thing 2 months ago, when it enters the feature store, it should already be part of the ETL that would be updated together with all the other features. So that's how it maintains. Does that address your question? Okay, cool. Okay, 22 seconds left. Anyone else want to ask a question? I guess no. Well, thank you everyone for joining this session, and I hope you find this to be useful.
Thank you so much.